In this lecture, we take some example of Cayley-Hamilton theorem. Question is verify Cayley-Hamilton theorem for the matrix A is equal to 1, 4, 2, 3 and find its inverse. Also express a to the power 5 minus 4 a to the power 4 minus 7a cube plus 11a square minus a minus 10i as a linear polynomial in A. So let us try to simplify it or solve this question. So according to Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. We have to verify the Cayley-Hamilton theorem for the matrix A is equal to 1, 4, 2, 3. The characteristic equation of A is given by A minus lambda I equal to 0 or lambda square minus S1 lambda plus determinant of A equal to 0, where what is S1? S1 is nothing but the sum of diagonal elements. So 1 plus 3 is equal to 4. Determinant of A is nothing but the determinant of 1, 2, 4, 3. So 1, 3 is 3 minus 2, 4 is 6. So 3 minus 6, which is, sorry, 4, 2 is 8. So 3 minus 8 is equal to minus 5. If we substitute all these values in equation number 1, we have lambda square minus 4 lambda minus 5 equal to 0. This is the characteristic equation of the given matrix. Now, according to Cayley-Hamilton theorem, that every square matrix, so A is a square matrix over here, and the matrix A will satisfy this equation. So this is characteristic equation of the given matrix A. Hence, by the Cayley-Hamilton theorem, we can replace lambda by A. So A square minus 4A minus 5I equal to 0. This is called Cayley-Hamilton theorem. Now we have to prove that A square minus 4A minus 5I equal to 0. Now we have to verify the Cayley-Hamilton theorem for the given matrix A. So let us first take the left hand side. And if we put all the values of left hand side, ultimately it should be 0. Then we say that the Cayley-Hamilton theorem is verified. Now here what is A? Let us compute A square is equal to A into A, which is nothing but 1, 4, 2, 3 into 1, 4, 2, 3. If you multiply this, 1 into 1 is 1, plus 4 into 2 is 6, and so on. We have the answer 9, 16, 8, 17. Now consider left hand side, which is nothing but A square minus 4A minus 5I, and if you put the value of A is nothing but 9, 16, 8, 17 minus 4, 1, 4, 2, 3 minus 5, 1, 0, 0, 1, because it is the identity matrix, the last one. If we simplify it, 9, 8, 16, 17 minus 4 minus 60, 4, 16, 4 2 is 8, 4 3 is 12, 5, 0, 5, 0. Now, if we write down 9 minus 4 minus 5, 16 minus 16 minus 0, 8 minus 8 minus 8 minus 0 is 0, and then 17 minus 12 minus 5, which is again 0. So we are getting 0, 0, 0, which is equal to 0, which is equal to right hand side. It means that the given matrix A satisfies its own characteristic equation. Therefore, A square minus 4I minus 4A square minus 4A minus 5I is equal to 0. Hence, Cayley-Hamilton theorem is verified. This is the first part of this question. Let us take the second part of the question. We have to calculate A inverse. Now we have to calculate A inverse. So from the equation number 2, determinant of A equal to -5, which is not equal to 0. Hence, the given matrix is non-singular, so A inverse exists. Now operating A inverse on both the sides of 3, we have A square times of A square minus 4A minus 5I equal to A inverse. And this A inverse A, 4A inverse A minus 5A inverse, which is equal to 0. So this is A inverse A is nothing but I. A inverse A is nothing but I. So we have the answer A, sorry, minus 5A inverse, and we replace this to the right hand side, minus A plus 4I. A inverse is equal to minus 1 by 5, minus is multiplied on both the sides. So 1 by 5 times of A minus 4I, which is equal to 1 upon 5, 1423 minus 41001, and which gives us 1 by 5 into minus 3, 4, 2 minus 1. Therefore, A inverse is equal to 1 by 5 times of minus 3, 4, 2 minus 1. Now, we have to express A to the power 5 minus 4, A to the power 4 minus 7 A cube plus 11 A square minus A minus 10 I as linear polynomial in A. So for this purpose, we have to just consider about the equation. Now, we know that by equation number 2, A square minus 4A minus 5I, which is equal to 0. Now, what we can write down over here, A5 minus 4A to the power 4 minus 7A cube plus 11A square minus A minus 10I. Now, what I am doing over here, A to the power 5, A to the power A 4 into A to the power 4, we are not touching anywhere over here. This 7A cube can be break down into two parts, 5 and 2. 11 is also break down 8 plus 3. Then what is the next part? Now A to the power 5 minus 4A to the power 4 minus 5A to the power 3 minus 2A to the power 3 plus 8A square plus 8A is 3A square plus 10A minus 11A minus 10. And if we simplify again it, what we can write down over here, which is equal to A to the power 5 minus A to the power 4 minus 5A cube minus 2A cube. Where is the 2 cube? This is 2A cube plus 8A square plus 10A plus 3A square minus 12A minus 10. So what we are doing over here, A to the power 5, we have A to the power 3 we have taken outside. So here A square is remaining. Here minus 4A and minus 5I, the first part. If we take 2A as common in this 3 part, the A square minus 4A minus 5I plus 3 times of, from here, 3 times of 3 we have taken outside. Remaining is A square minus 4A minus 5I plus A plus 5I. Just look here, A square minus 4A minus 5I, which is equal to 0. a square minus 4a minus 5i equal to 0, and a square minus 4a minus 5i, which is also equal to 0. So we are getting a plus 5i. So this complicated equation is converted into very simplest equation, a plus 5i. Therefore, a to the power 5 minus 4 into a to the power 4 minus 7a cube plus 11a square minus a minus 10i, which is nothing but a plus 5i. This is linear polynomial in A. Thank you.